Let's discuss a question from counterflow heat exchanger. So what we are asked is to find out the log mean temperature difference in this setup. So it's a counterflow heat exchanger. So let me just draw a simple so here you have the cold water entering. So and here you have, because it's a counterflow heat exchanger, so hot water will enter from the other end. Okay, and so this is state 1. I'm just calling this as state 1 and this as state 2. Okay, so now the log mean temperature difference, if you recall the formula, it is just defined as this is a parameter which plays an important role in calculating overall heat transfer coefficient. It appears in the expression of overall heat transfer coefficient. But what does log mean temperature difference mean? It is the difference in the temperature at the inlet minus, the temperature difference at the inlet minus the temperature difference at the outlet by the logarithmic ratio of the temperature difference. Okay, now in order to calculate this, you need to know all the temperatures at both the inlets and both the outlet. But going by the figure, we know the cold water inlet and outlet temperature, whereas hot water we know the inlet but the outlet is missing. This is what we don't know, right? So for this, because the general thing is that we assume that the energy carried by the hot water, the energy given by the hot water, the entire energy is used for heating cold water. So the change in internal energy or enthalpy, because it's a flow stream, so change in enthalpy of the hot water, basically the decrease in enthalpy of the hot water is increase in enthalpy of the cold water. And how do we write enthalpy? Enthalpy is always given as, enthalpy of these liquids is always given as mcp delta T. So mass into specific, so mass of hot, specific heat of hot water into the decrease in the hot water temperature. So T, I would say T out, T inlet will be more minus T out for hot is equal to mass of cold and specific heat of cold, may I see only, by that, because the temperature will increase, so T out minus T in for cold. So this is basically the enthalpy change, which is always written as mcp delta T for liquids. So mass of hot water is given as 2 kg. It's represented in the figure. The specific heat is 4.31 and the outlet temperature is, the inlet temperature is 160. The outlet will be less than this because it gives out heat. So T out of cold is equal to the flow rate for the cold is given as 1.2. The specific heat is 4.18. The temperature of the cold is given as 80 and outlet, and the inlet is 20. So this is one expression which, once you know all the three temperatures, the other temperature, the third, or the, if you know, you need to know three temperatures, and the other temperature you can get by this energy balance. So in heat exchange terminology, we call this as energy balance. So the T out from this comes out to be 125 degrees Celsius. Okay, so now once I know all the temperatures, I can use this formula to calculate. So LMTD is delta T1 at the start. So delta T1 here, the cold water inlet is 20, and outlet is 80, whereas the hot water outlet is what we got as 125, and this is hot water inlet is 160. So you can take either delta T1, the difference here is 125. You have to take a positive difference. So 125 minus 20 becomes 105. So delta T1 is 105, and delta T2, which is the difference at the second. Now 1 and 2 can be, you can consider this as 1, the other as 2, the LMTD value will not change. It's just it will be negative in the numerator, negative in the denominator, and it will cancel out. So 160 minus 80 will be 80. So delta T1 is 105, delta T2 is 80, and this becomes ln 105 by 80. So even if you consider this end as 1 and this end as 2, in the numerator it will just be negative, and the denominator also it will be negative, so the value will remain same. So if we calculate this we get a value of 92. So this is our easy problem which combines both energy balance as well as the LMTD concept. Thank you.